In solving the thermal equilibrium for the solar corona, we assumed that the heat conduction was given by plasma electron conduction, and that the conductivity of heat scaled with the temperature only, as the -5/2 power, or as, in some senses, as the temperature to some power b. This was for a condition, as I said, of electron conduction, the physical motion of electrons carrying the heat from one part of the solar corona plasma to another. What are other ways that the conductivity of heat can vary with our thermodynamic variables rho and T? Well, when radiation dominates in particular, the opacities can depend on the density and temperature, and this can lead to a heat conductivity that itself is a function of the density and temperature. If that functional form of the way that the heat conductivity K depends on rho and T takes the form of a power law, rho to the A, T to the B, then we call this a Kramer opacity. Or heat conduction by radiation under a Kramer approximation. Now, Kramer opacities are very convenient. They end up giving us a closed system that we can solve for hydrostatic and thermal equilibrium, as we will see in just a moment. Before that, let's note that especially if we're dealing with an atmosphere of a planet, we may actually want to write the Kramer opacity in terms of two other thermodynamic variables, P and T. Remember, for any three thermodynamic variables, rho, T, and P, only two of them are independent, and the third is determined by the equation of state. And so for the Kramer opacities in P and T, this is P to some, say, alpha, and T to some beta. And the alpha and the beta of P and T are related to the A and B of rho and T if we're dealing with an ideal gas, though that is not necessary for the assumption being made here of a Kramer-like opacity. Okay, so why is this interesting? So if we assume hydrostatic and thermal equilibrium for a gas that is dominated by Kramer opacities, we end up with the following system of equations to solve. So we have our momentum equation and hydrostatic balance. So that's that grad log P is equal to G over RT. And we have that the div of K grad T is equal to 0. But we have a functional form for our K here. We can replace this and use our P and T form. So that's P to the alpha power, P to the alpha, T to the beta. And this is a closed nonlinear system of equations. There are two equations, two nonlinear equations. There are two variables here, P and T, and with two equations, two variables, we can actually solve this as a nonlinear boundary value problem. Call these an NLBVP, a nonlinear boundary value problem. If we know something about the values on the boundary of pressure and temperature, then we can solve in the interior and get the atmospheric solution. Often we'll know the temperature and pressure conditions at infinity. We might know that they tend to zero or something like that, and we then can choose a reference point in the atmosphere, a reference level where we specify a pressure and a temperature, and that can give us a full solution. That reference level might be something like ground level at Earth, or sea level at Earth. And in a star, that reference level might be something like the photosphere, a point where we transition from an interior that's opaque to radiation to an exterior that's transparent to radiation.